two parts. All right, so the second part, what we're going to look at is what you call a absolute, or often called global extrema. So there's a difference between local extrema and absolute extrema, and it's pretty simple what the difference is. So we're going to go ahead and talk about that first of all. Okay, so we're going to look at some graphs to kind of get the idea. So this is what your technical definition is right here. So you're going to have an absolute or a global minimum. What that means is it just means in words, it's the absolute lowest value of y that you ever hit on an interval. You might have several minimums throughout your graph, but the absolute minimum is the lowest that it ever hits. And what it means in the definition, it just means this function is smaller or equal to every other function value. So it just means if c is your absolute minimum, it just means it's less than or equal to every other function value there is. And it's key that it has a less than or equal. An absolute or global maximum just means, and f of c is your global maximum, it just means it's greater than or equal to every other function value. So in words, it's just the absolute highest and the absolute lowest. Okay, that's what it means. Okay, so and then typically we call, if we have more than one maximum, we call it maxima and minima. That's just the English of how a plural if you have more than one. All right, so what I kind of put of in basic terms without being too technical, the absolute minimum on an interval is going to be the smallest function value that ever exists. And it could be a tie. You could have several absolute minimums or maximums if it's the same value. And the absolute or global maximum will be the biggest function value that you have. Okay? One thing that's pretty important on this, if you have an absolute extrema, it can be on an end point. When you have a local minimum or maximum, that can't be at an endpoint. Okay, so this could be an endpoint when you have that. All right, so I'm going to go through just this first example, and we'll kind of look at what it looks like on a graph. Okay, so first of all, this is the graph of y equals x to the second. That's a parabola, and the interval is negative infinity to infinity. So what would happen if you graphed x squared? You would not have an absolute max. The reason you don't have an absolute max is because it gets bigger forever, right? Okay, so you're not going to have an absolute max, but you would have an absolute min, and that absolute min would occur at 0. What we typically say is when we write an absolute min, we usually give the y value as the answer, and then we also would say when x is 0. Okay, that's the way I typically like you to do that. So I know on the homework that I'll be putting up on web work, I've been putting problems that will be pretty specific about whether they want the y value or x value. Okay, so typically we just give the y value and then we state whatever that x value is. Okay, the next one is the same graph, but I'm changing the interval. It's a closed interval from 0 to 2. Okay, so you're only looking at part of the parabola. So this part right here, that would be your absolute min. And again, the y value is 0, x is 0. That's the absolute lowest value of y that you ever hit. And then this right here would be the absolute max. That is the biggest y value on that interval that you have. Okay? So that's the idea. Real simple. Absolute just means the biggest there is or the smallest there is for min and max. Okay? Okay. Next situation. These are a little bit trickier. So what happens on this problem, it's still y equals x squared, but now you're open at 0 and then you're closed at 2. So what this says on your graph is you would end up having a closed dot there, and then you would end up being open there on that interval. So we're doing the interval from 0 to 2, but we're having a bubble on 0 because there's a parenthesis. Okay, that's what that means. So what you would have in this case is you would have an absolute max. That would be the absolute highest point. That has a y value of 4 when x is equal to 2. So you usually just say, give me the y value, then the x value like that. That's how you name that. Now, what's weird about this is there is no absolute min. Okay, the reason there's not an absolute min is because this function never goes to 0. It just gets infinitely close to 0. I mean, you might end up getting y equals 0.000001, but you never hit 0. So for that reason, there is not an absolute min. So if you got an open bubble, that cannot be an absolute min or max because it's undefined. Okay, you have to be defined in order for it to be one or the other. Okay, what happens on this last example is both are open. So again, we're just graphing the quadratic function y equals x squared from 0 to 2, but we're open at 0 and we're open at 2. So what that would mean is there is no absolute max because this graph never reaches 4. It may get to 3.999 forever, but it never hits 4. Okay, you can never find a biggest value of this function. In other words, kind of think of it this way: if you can never get the number that's right to the left of 4. There is no number, because the decimals go on forever. So there's neither an absolute max or a min. Okay, does that make sense so far? So just try to keep the definition simple. In order for something to be an absolute max, number one, it has to be solid, has to be a solid point, and it's just the highest value of y that there is. In order for something to be an absolute min, it's got to be solid, and it's just the smallest value of y that there is on the entire interval. That's what that means, okay? Okay, so I'm going to let you do these 4 problems, okay? Just kind of, and what you'll do is I want you to just give me x values on this because I didn't give you y values on these graphs. So all you're going to need to do is just tell me where you think the absolute max is, what x value, and what you think the absolute min is. If there's none, write none, okay? So I want you to do, there's 4 problems. There's these 2 at the bottom of the page, and there's the 2 at the top of the page like that. Okay, so I'll give you a couple minutes to kind of reason through that. The thing that you have to be careful about is the open bubble, okay? And some of these are going to have solid dots. Some of them are going to have open bubbles. And the absolute min and max, it can be anywhere. It could be at an endpoint, or it could be somewhere in between the endpoints of the interval. So I want to just give you a minute to see if you can reason that out. And I'm not going to really check your work too much. I'm just going to kind of walk around and kind of see where you're at. Shouldn't take you very long to probably do this. Just give me the x values. And sometimes you're not going to have any max or min. You may have none on some of these, just like what I was doing before. Okay, all right. I'm not going to give you a lot of time to do that because not much to do on this. So go back to A. Does this thing have an absolute max? What's the x value of the absolute max? B. Okay, that's your max. That's absolute max. So that happened at B. Does it have an absolute min? Not A. C2. Okay, that is your absolute min right there. Okay, that endpoints, that's not the lowest value. So it's got to be the lowest value that ever happens on the graph. Okay, so you got that. Okay, how about part B? Where is the absolute max? That's C, good. Okay, how about the absolute min? You don't have one. Okay, this is not the absolute min because it's an open bubble. So you have none there. Okay, let's keep it real simple. Absolute max is the highest point. Absolute min is the lowest point. Okay, make it real simple. And it doesn't have to be at endpoints. Okay, some of you might not have caught that. Okay, next page. How about part C? What do you think about the absolute max? There's none. How come there's none? There's a bubble there, okay? So that does not count as an absolute max. You're never going to reach a definitive high point on that graph. You'll get infinitesimally close to that bubble, but you'll never hit it. So there isn't one. Okay, how about the absolute min? That's A, okay? That's a solid dot. So you do have an absolute min there. That happens at A like that. Okay, high point, low point, that's all it is. Okay, how about part D? What do you think about absolute max? It's at A, but right there, that solid dot is your absolute max. That counts. It doesn't matter if there's a bubble there. That is solid, and that is the biggest, the highest value on the graph, so that's A. Okay, how about absolute min? That's C, good, okay? And it doesn't matter if there's a sharp point. That has nothing to do with it. Okay, it is a definite point on the graph. There's not a bubble or anything, so you end up having that at C. Okay, is everybody okay with what you did there? Yeah. Okay, because that is not the biggest value of Y. See, all of these things right here are higher up, aren't they? Okay, that's why. Okay, if I was looking at C to B, if I was looking at the interval C to B, then C would be the absolute max. But the thing is, you got a bunch of points that are an infinite number of points that are higher up than that one is. That's why. Okay, any other question? Okay. Okay, so a couple of things just kind of to mention here. So first of all, a local extrema, we've already talked about that earlier in the notes for 2.7a. A local extrema never occurs at an endpoint. An absolute max or min can occur at an endpoint. Okay, you've seen that in the previous examples. Okay, now a local minimum occurs whenever the function decreases and then increases. So your sign chart, whenever you have a local minimum, you would have this critical number, and then you would end up having a decrease and then an increase. Okay, that's when you're going to have a minimum, is whenever the graph decreases, then increases, like we talked about earlier. You have a local maximum occurs when the function increases, then decreases. So if you have a local max, then your sign chart's going to look like this. You have your critical number, you have a max. It's just going to mean that you're increasing from the left, and then you're decreasing to the right. Okay, and it can't be an endpoint because there has to be something that happens on either side of the critical value. So local min and max are a totally different concept than an absolute min and max. That's the idea. Okay. So if you were to look at like this graph right here, these right here this would be a local min there. This would also be a local min here because the graph is going from decrease to increase, okay? And then these points right here would be local maximums like this because the graph is increasing from the left and then decreasing from the right. Okay, now see these 2 points right here would also be absolute maximums. Okay, the reason those two things are absolute maximums would be because that's the absolute high point you have. Unless you consider this graph to go down forever, and I'm not really considering it that way. And then these 2 points right here would also be absolute minimums because they're the lowest point that that graph ever reaches. Okay, so there's a difference between local and absolute. Does that make sense? Okay, all right. So kind of a couple other situations. This is just a good overall view of this. Okay, you'll see I usually use the word absolute, global, means the same thing as absolute. So this would be your absolute highest point. That right there is a global maximum or an absolute maximum. This point right here is a global or absolute minimum, okay, because that's the lowest point. And then something like this would be a local max right there, and that right there would be a local min. Okay, and the difference between that is the local maximum has to go from increase to decrease, and the local minimum has to change from decrease to increase. Okay, so that picture to me summarizes the difference between the two. Now this right here would also be a local min. And the reason it would be a local min is because the graph decreases then increases. So that would be both local and global at the same time. Okay. This one, however, would not be, this is not a local max. Does anybody know why that's not a local max? It's an endpoint. Okay. And remember, a local max has to go from increase to decrease. It cannot be an endpoint. That's why. Okay. So that kind of gives you some of the different situations. All right. Now, last thing on this, these are just a couple of more graphs that you can refer to. These are like on an interval negative infinity to infinity. So this point right here, you would have this right here would be a local max, okay, because the graph increases then decreases. This point right here would be a local minimum because the graph decreases then increases, but you would not have an absolute max or min. Why would you not have an absolute max or min on that graph? Because it goes on forever, right? Okay, you got these arrows right there. That means the graph gets higher forever, and that arrow right there means the graph gets lower forever. So there is no absolute high point or absolute low point, okay? The range of that graph is negative infinity to infinity. Okay, this next example, that would be a local maximum, but it would also be an absolute maximum. Okay, so it's both at the same time. That's the absolute highest point, and it's a local max because it changes from increase to decrease. That's just real picky details, but that's what it's saying. Yes? Well, it just depends on what you're asked, like on a problem, what you're asked for. Typically the way I'm going to ask that is, here's a graph, tell me where the local max and mins are. Tell me where the absolute max and mins are. But it's important to know that they can be both, okay? Okay, and what happens on this last one, that point right there would be a local min, and it would also, at the same time, it would also be an absolute min. Okay, because that's the absolute low point. It's local because it changes from decrease to increase. Okay, so you just got to make sure that you're real clear on the difference between what local and absolute are. Okay, all right, so just think of local as either the graph increases then decreases or decreases and increases. That's what they are, okay? But absolute just means the highest or lowest on a graph. Okay, now, next thing I want to show you is what we call the extreme value theorem. This kind of leads up to the calculus we're going to be using to identify absolute or global maximums and minimums. So what the extreme value theorem says, it says that you have a function and it must be continuous on a closed interval. So it has to be continuous on a closed interval. And what this theorem says is if you have a function on a closed interval and it's continuous, then you absolutely must have an absolute max and an absolute min. You have to. You are forced to have that. That's what this theorem says. So let me give you a couple of graphs down the bottom that I want you to write out and just give you a couple of situations. So let's take a point like this point right here and label that the point -4, -2. Make sure that has a solid dot on it. Okay, and then let's pick a point over here. Let's use the point 0.42. So what I'm doing is I'm closing the interval. Now, if I was going to connect those two dots, one way to connect these two dots would be like this. with a straight line. Now that's continuous, so I drew a continuous function, no breaks in between. Does that graph have an absolute max? Yes. What is the absolute max? What point? Or 2. Does that graph have an absolute min? Yes. Okay. So the theorem says that you have to have one of each. Okay. So what you have is this would be your absolute max. This would be your absolute min. Okay. That's just one scenario like this. Okay. Okay. Let's do another example. Let's say that you have the point negative 5,3. And let's say you have the 0.53. It doesn't matter what points you're using on this. The idea is it's closed. You couldn't have an open bubble on that. It's got to be closed. So there's all kinds of ways to connect those two dots. You could connect this like this. Okay. All right. Does that have an absolute max? Where's the absolute max? I tried to draw it so it's at a whole number. Probably right there. Okay, that looks like that right there would be your absolute max. Okay, does this graph have an absolute minimum? It looks like it probably happens at -2. Okay, so you have an absolute min. So the extreme value theorem says that if you have a continuous function and you're connecting two solid dots, then you have to have at least an absolute max or an absolute min. Okay, you could have more than one, okay, but you're going to be forced to have one. Another situation is something like this. Let's do something like the point, say, -4,4, and then let's put the point +4,4 like this. Okay, another way you could connect these two dots is with a horizontal line. Okay, now that's kind of interesting. Does that have an absolute max? Does it have an absolute highest, biggest value of y? Yeah, 4 is the biggest value, right? Does it have a smallest value of y? Yeah, they're both 4. So actually in this thing, you have every point, this is kind of weird, every point is both an absolute max and an absolute min at the same time. Now, the reason for that is, if you go back to the definition of an absolute max, is that an absolute max means it has to be, the y value has to be greater than or equal to every other point. And the fact that the definition allows for equality means that in that case, every point has a y value of 4, so it's an absolute max and absolute min at the same time. Does that graph have any local mins or maxes? No, because remember, local has to either change from increase to decrease or decrease to increase. So it doesn't have any for that reason. Okay, the details of this are kind of picky, but once you wrap your head around the definition, it's not too bad. Okay. Okay, on this next page, just kind of want to look at the extreme value theorem. And again, what the extreme value theorem says is if your function is on a closed interval and continuous, then it guarantees that you have to have an absolute max and an absolute min. At least one. You have to have at least one. Okay, so look at this graph right here. Is this a closed interval? All I mean by that is, are the endpoints solid? Yes. Okay, so what you would get on this is it is closed. Okay, now the other question is this continuous? Is that graph continuous on the whole thing? Yeah, there's no breaks. Okay, so that would mean that yes, that meets the conditions of the extreme value theorem. What does that mean? It means that that graph is guaranteed to have an absolute max and an absolute min. Okay, does it have an absolute max? Yeah, where's it at? At A, that's your absolute max. Okay, so that happens at A. Does it have an absolute min? C, yes, right there. Absolute min, what happened at C? Does that problem have a local minimum? Yeah, local minimum would be right here also. That's local as well because it decreases then increases. Okay, does this graph have a local maximum? Yeah, okay, right there would be a local max because the graph increases, hits a high point, then decreases. The locals are all about increase, decrease. Okay, absolutes are just what's the absolute biggest or absolute lowest. That's the difference. Okay, okay, so let's take a look at this one. Would you consider this to be a closed interval? No. Okay, there are bubbles at the end. Would you consider this graph to be continuous? No, there's a break in the graph. So this does not meet the conditions of the extreme value theorem. So if it doesn't meet those conditions, then generally what it's going to say is you don't have to have a max or absolute max or min, but you might have one or the other. Okay, so there's all kinds of ways to draw a graph that doesn't, if it doesn't have the extreme value theorem, you're not going to have both. Okay, you might have one or you might have none. Okay, does this thing have an absolute max? Yeah, right there. Okay, that would be your absolute max. So that happens at C. Does this have an absolute min? No. Although that may look like the absolute min to you, why is that not an absolute min? Well, it's open. So you never ever reach a low point on this graph. You just get close to it. Okay, so there is none there. So that's what's going to happen if the extreme value conditions are not met, is you might have one but not the other. But if they are met, you're going to have both. That's what it says. It's a guarantee. All right. Okay, so now what we're going to do is kind of put this together. I want to kind of get through some problems where we have a given function and then we use calculus to identify local max and min. We've already talked about what a critical number is. A critical number is going to be an interior point, and that means not endpoints. Critical numbers are never at endpoints. That's just where the derivative is zero or the derivative does not exist. That's not new to us. We've talked about that already. If I ask you for a critical number, that's what you're looking for. Okay. And again, critical numbers don't happen at endpoints. All right, now what we're going to learn how to do is how to find absolute or global extreme values on a closed interval. So these are going to be the three key steps that you're going to need to do. So the first thing that you're going to do is you have to make sure the function's continuous and closed. If it is, then you do this methodology. What you do is step one, find the critical numbers. Okay, step two, you're going to evaluate the critical numbers and the endpoints. You're going to plug those into the original function. And then step three is after you've evaluated the endpoints and critical numbers, then the largest function, of course, is going to be the absolute max, and the smallest is going to be the absolute min. Okay? Now, I'm going to do some examples that are going to take you through this three-step process, okay? And then you'll understand why this works. This is basically what the extreme value theorem tells us we can do, okay? Okay, so let's start pretty simple here with this one right here. Okay, so I'm giving you the function x squared minus 10, and I'm giving you the interval. I'm always giving you an interval on these problems, -2 to 3. Question number one, did I give you a closed interval? Yeah, how do you know it's closed? Because there's brackets, okay? If there was a parenthesis on one of them, then you wouldn't be able to do that. It wouldn't follow the extreme value theorem. How about x squared minus 10? What does the graph of x squared minus 10 look like anyway? It's a parabola. Is that continuous everywhere? Yeah, there's no breaks on a parabola, so it is continuous. So that means that it does satisfy the extreme value theorem. So what we're going to do is we're going to do critical numbers, all right? So what do I need to do to find a critical number? Take the derivative, and what is that derivative? 2x, okay? And what do I do with that derivative? I set it equal to 0, okay? So you set the derivative equal to 0 because a critical number is where the derivative is 0. And you solve that equation, you can do it in your head. So you get a critical number at x equals 0. And that's the only critical number you have. Okay? Sometimes you'll have more than one. Sometimes you'll have none. It just depends on what the derivative is. Okay, and you're never undefined. The derivative's 2x. 2x is a linear function, it's a line, so 2x is never undefined. Okay, so that would be your only critical number. Okay, now here's what you do next. What you do is you work with the endpoints of the interval, -2 and 3. And what you're going to do is you're going to plug those into the original function. So we're going to do f of -2, and we do that just by plugging into the function. So we do -2 to the second minus 10. That would be 4 minus 10. That would be -6. Okay, so you just find the y value of the endpoints. Okay, then you want to do f of 3, which is the other endpoint of your interval, so that you're going to do 3 to the second minus 10. That's 9 minus 10. That's -1. Okay, so we need to look at the endpoints first. Then we're going to look at the critical numbers. Okay, so now we're going to do f of 0. The only critical number we got was 0. So you're going to plug 0 into the original function. So that will be 0 squared minus 10. That's equal to -10. So really what happens is you're going to, since this follows the extreme value theorem, this means that we're guaranteed to have an absolute max and an absolute min. And where they're going to happen is either at the endpoints or some place where the tangent line's horizontal. Okay, now all you got to do is this, and this is super easy. The smallest number is this right here. So that would be your absolute min, right there. Your biggest number is -1, so that would be your absolute max. So once you do that, always do the endpoints and critical numbers, because the absolute max and min can only happen at those places. It can't happen anywhere else, okay? So what you would do is when you write your answer, typically we write the answer like this. You would just say absolute max is equal to -1 when x is equal to 3. That's the way I usually like to do it. Now on a test, I might say give the y value. I may say give the x value. That's just kind of the standard way that most textbooks do that. And then for the absolute min, we would write our answer as the y value, which is -10, when x is equal to 0. Okay, so that's how you basically do that problem. All right, so basically it's always critical numbers and endpoints. Find out which is the biggest and which is the smallest. That's all it is. All right, does that make any sense? Okay, now on the graph, I think I put this graph on your handout. What you find is this point right here is the point 3, -1. That's where your absolute max was. And this point right here was 0, -10. That's where your absolute min was. Okay, so you can always tell on your graphing calculator if you're right. And what I did on this is I just graphed the function from -2 to 3. You don't have to look at anything beyond the closed interval -2, 3. That's how you figure that out. Okay? All right, does that make sense okay? Okay, any questions? Okay, so the problem gets a little bit harder if the derivative's a little bit harder. So let's do one more. I guess this should be example 4. So first of all, on this problem, did I give you a closed interval? Yes. Are we continuous? Well, the thing on this is, all you ever do is kind of think about, is there any value of x you would plug in that would make this undefined? You would never get a 0 denominator, right? You would never get a negative number under a radical. So no matter, you can take any number that you can think of and add 1 to it, and then raise it to the 4/3, you're always going to get an answer. So that is yes on both. So that means this methodology will allow us to figure out what the absolute max and min is, okay? Okay, so what we do is we move on to the critical values. And what do you do to find critical values? Critical numbers. You do the derivative, right? This is a chain rule. So when we do our derivative, It's going to work kind of like a power rule. We're going to bring the 4/3 down, subtract 1 from the exponent. You can do it in your head. You would really be subtracting 3/3. What else do you have to do on the chain rule? Derivative of the inside, the derivative of x plus 1 is 1. So if you forgot to do the chain rule, you just luck out and be right, okay? But I want to emphasize that always when you do that then. So we get 4/3 x plus 1 to the 1/3 power would be that. Now, one of the reasons I always like you to change things back into radicals and stuff is because of what we do when we find a critical number. So I would go ahead and change that to 4/3 times the 3rd root of x plus 1. Okay, now there's going to be some algebra issues. When you set your derivative to 0, there may be some issues that pop up with you from time to time. Okay, so what we want to do is take that derivative and set that equal to 0. Now, one thing that's always good is you can do this in your head. I mean, what value would you plug in for x that would make the whole thing 0? -1, right? -1 plus 1 is 0. Cube root of 0 is 0. 0 times 4/3 is 0. Okay, so you can do it in your head. I'm okay if you do it in your head. The way you would technically solve this algebraically is you would multiply both sides by 3/4, and what that would do is that would isolate the cube root from both sides. So you would have the cube root of x plus 1 is equal to 0. Now, what you typically learn in college algebra is if you solve an equation with a square root in it, you square both sides to get rid of the radical. If it's a cube root, you cube both sides to get rid of the radical. Okay, so what I would do now is this. Okay, and it's good to know this in case you can't do this in your head. So when you do the cube root of something cubed, that takes off the radical, so that gives x plus 1 equals 0. And then you would just get x equals -1. So that is your critical number right there. That's the only one. That derivative is defined everywhere. You can have any number under a cube root. Any number. You can take a cube root of negative number. So that is the only critical number on that problem. Okay? All right. So that's our critical number. Now let's finish up the problem on the next page. So what we want to do, let me write down what the function is. The function is x plus 1 to the 4/3. You can certainly use your calculator on this if you want to. So what we do is we do the endpoints first of all. So we're going to work with the endpoints. So you're going to work out g of -9. So just plug in the endpoints. So that's going to be -9 plus 1 to the 4/3 power. And that would end up being -8 to the 4/3. Now, you can do this on your calculator if you want to. I'll show you how to do this without your calculator. What this really means is the 3rd root of -8, then raised to the 4th power. That's what that means. We've learned how to change those things back. The cube root of -8 is -2. And then if you take -2 to the 4th power, you're multiplying -2 out 4 times. That would give you 16. Okay? You don't have to do it that way. I would sure like students to be able to do it that way. But you could also just go parentheses, -8, raised to the 4/3 power if you needed to do that, and I'll give you 16 anyway. Okay, so that's what's going to happen. Okay, and then we're going to do g of 7, which will be pretty similar. You're just going to do 7 plus 1 to the 4/3. So that would be 8 to the 4/3. And that would still be 16. If you look at that the same way, you could even do that on your calculator. 8 to the 4/3 is going to give you 16. Okay. Now what you need to do is you need to do the critical number, and the critical number was -1. So you're going to do g of -1. So now just plug -1 into the original function. You get -1 plus 1 to the 4/3. That is 0 to the 4/3. So that is equal to 0. Okay, so see what you're always doing is plugging the endpoints and the critical numbers into your function. Now, it's easy to answer the question, okay? What is the smallest? The smallest is 0, so that would be your absolute minimum. What is your biggest? Well, your biggest is a tie. So your absolute max would be both of those, okay? You can have the same absolute max. You can have more than one. It's just 16 is the biggest value. So what would happen is when you write your answer, you'd write your answer typically like this. You would say absolute max is equal to 16 when x is equal to -8 or x is equal to 8. No, that's not right. Why am I doing that? What did I plug in? I plugged in -9 and 7. So when x is -9 and x equals 7. Okay, so that's your absolute max. And then your absolute min is going to be 0 when x is equal to -1. Okay? Now what would happen on this problem is like on this graph I gave you, this is the point right there. That point is 716. This point right here is -916. And then this point right here is -10. So if you graph that function on your calculator, you can tell you're right. Okay, but again, the idea is learning how the calculus and the extreme value theorem works for us. Okay, you can't go by graphing calculator. Sometimes looks are deceiving, but calculus is always perfect and not deceiving. Okay, so don't go by looks, but you can use your calculator to check that. Okay, so that'll get us through most of this. We'll finish this up then next time. So bring this next time, and then we'll learn about concavity. So we'll kind of go backwards to 2.6.